today we're looking at similarity. Similarity is very similar to what we did with congruent figures. In congruent figures, we have the same size, same shape. All angles are the same, all sides are the same. They're all congruent. However, with similar figures, we say we have the same shape still, all the angles are still congruent. However, all my sides are no longer congruent. We can have different sizes. They just need to be proportional to each other. So, just to see what this looks like, I have these two triangles here. First, the question is, do I have 3 pairs of congruent angles? Well, I have 2 marked, my X and A, my C and Z. However, what about the third angle? Well, third angle theorem tells us if I have 2 of the angles, then I must have a third. So I have my 3 angles, that's good. Now, to check for proportionality of size, I'm going to start always with the smallest side of my first triangle, which is 6. If they are similar, then the smallest side of my other triangle, which is 3, those should make a ratio that is equal with the other one. And what I mean by the other one, so after I do the first one, let's now look at the second biggest side, which is 10 and 5. They should make the same ratio when I do 10 and 5. And the same thing, the last one, which is 14 and 7. 14 and 7. If they are similar, then all of these should be the exact same fraction. Well, 6 over 3 reduces to 2 over 1. This reduces to 2 over 1, and this reduces to 2 over 1. Those are all the same fraction. We can actually call this right here our, we're going to call it our proportionality ratio, or similarity ratio. 2 different words for the same thing. That's what we're looking at. And now because the ratios are all the same, I do have similar triangles, so I'm going to make a similarity statement. If I say triangle ABC would be similar to what? Well, ABC goes 1 angle marking to no markings to 2 markings. I need to do the same down here. X, Y, Z goes from 1 to 2 to none. Here's another example to look at. We're going to say the exact same thing. Again, do we have angles? 3 angles. Yes, we do. 2 that are marked, and the third angle theorem tells us the last one. So we'll set up the same exact thing we did before. Start with the smallest for both sides. So I'll have 16 over 12. It should be the exact same as, let's make my next one be the next biggest, which is 20 and 15. 20 over 15. And then my last one is whatever is left over, which I will have here 24 and 18. So 24 over 18. Are those all the same? You can do it by trying to reduce the fraction or by just putting in your calculator and dividing. I divide both top and bottom here by 4 if I reduce. I get 4 over 3. Do the same dividing by 5 here. Gives me again 4 over 3. Dividing by 6 here. 4 over 3. Same exact ratio, same similarity ratio, so I have similar triangles. If I do triangle ABC this time, it would be similar to ABC but 1 to 2 to no markings. So DEF again, DEF, 1 to 2 to no markings. Alright, and this also works for quadrilaterals. So in this one, we have rectangles here. I'm going to first say, obviously, a rectangle, all the angles must be congruent. So we have the congruent angles portion, that's good. Now, same thing as before. The small side must go to the small side. So 4 over 6. It must be the same as when I look at the larger sides, which are 12 and 16. 12 and 16. Technically, I need to also look at these other 2 sides. Well, this would be 4 and 6 would go together. We already have that ratio. And 12 and 16, they would have to go together. But we already have that ratio. So really, I only need to check the 2 for this one. Now, I can divide by 2 and by 2 for the first. For the one in pink, gives me 2 over 3. If I divide by 4 and 4 here, I should get 3 over 4. 2/3 and 3/4 are not the same thing. Therefore, we're going to say that these 2 shapes are not similar. So we can do the same for quadrilaterals, just this one ends up being that they are not similar. There you have it, your crash course on similarity. Same size, different shape. One is an enlargement of the other, for example, and that's what we need to look for.